Hello everyone. Welcome back to this lecture series on Design of RCC Structures. This is a lecture 11 in which we are going to discuss the design principles of doubly reinforced beams along with a numerical example by using limit state method. Before going to this lecture, let me recollect whatever been done in the previous lecture. So in the previous lecture, we discussed the design of a singly reinforced beams using the limit state method, in which we learned that singly reinforced sections are preferred because of their ductile nature as well as economical. But however, there are situations where a singly reinforced beam is not sufficient. In such cases, we must provide the compression reinforcement, thereby the beam will behave as a doubly reinforced beam. So in today's lecture, we will understand why doubly reinforced beams are required, and we'll study the design philosophy, and finally we'll solve a complete numerical design problem. Now let us first understand the section details of a doubly reinforced beam. So in this beam, the concrete will tend to resist the compression, whereas the steel, which is provided both in the tension zone as well as in the compression zone. Here some of the important notations are, we'll have the Cu, that is the total compressive force in concrete, which will be calculated by using the relation CUC plus CUS. So what is CUC and CUS are? CUC is the resultant compressive force in the concrete, whereas CUS is the resultant compressive force in the steel. So that summation will be doing it for getting the total compressive force in concrete. That is the only variation in case of doubly reinforced section comparing to that of the singly reinforced section. Whereas the total tensile force TU will have the unique number, that is the same value what we have used in case of singly reinforced beam, that is 0.87 FY/AST. And these two will be separated by a distance Z, that is the lever arm. Here AST represents the area of the steel in the tension zone and AAC represents the area of the compression steel. So here the CUS and CUC will be calculated using these relationships. So once these been done, we will be calculating the total compressive force in concrete and then total tensile force in steel. And finally, we will be equating these two by using the force equilibrium conditions, thereby computing the depth of neutral axis as well as the moment of resistance for a doubly reinforced sections. So here the key concept to emphasize in this doubly reinforced beams is that both concrete and the compression steel will resist compression, while tension steel resists tension alone. Now let us go with the Codal provisions. IS 456 permits the use of doubly reinforced beams only when the depth of the beam is restricted. We can't able to increase the cross sections, maybe due to the architectural reasons. Second thing is that when the bending moment is exceeding the limiting moment capacity, that is mu is greater than mu limit. And finally, if there is any reversal of stresses is being expected, for example in case of continuous beams, in such circumstances this compression reinforcements may be allowed, thereby the section will behave as a doubly reinforced section. Now coming on to this compression steel, what is the role of compression steel in the doubly reinforced section is, it will increase the moment capacity of the beam, and also it will improve the ductility nature of the section, whereas it will reduce the long-term deflection, thereby enhancing the performance under a repeated loading. So here the formula has been given, and these are available in Annex G 1.2 of IS 456, which has been specifically given for section with the compression reinforcement. So it was clearly mentioned where the ultimate moment of resistance of section exceeds the limiting value mu limit, Compression reinforcement may be obtained, that is ASC can be obtained from the following equation, that is mu minus mu limit will be equal to FSC ASC into D minus D dash. So here mu and mu limit are already defined in section 1.1. ASC is the area of the compression steel, small d represents the effective depth, and small d dash represents the effective cover to the compression reinforcement. And finally, what is FLC is the design stress in compression reinforcement corresponding to a strain of 0.0035 into XU max minus D dash divided by XU max, in which XU max will be defined based on the section 38.1 for different grade of steel. This has been listed here. For example, if it is the grade of steel is Fe415, means that XU max will be 0.48 D, or XU max by D is equal to 0.48. The corresponding mu limit is also being given. Now moving on to the tension reinforcement. Here the tension reinforcement will be the sum of the reinforcement which has been provided for the balanced singly reinforced section, as well as the steel required for the balance moment due to the compression reinforcement. So here AST1 will be calculated assuming that it is a singly reinforced section, considering for mu limit. So in that case, we can go with the G1.1b, the formula which is available, in which mu will be replaced with the mu limit. That is the only variation to be done in that formula. Rest everything will be known. You can able to calculate the AST. That is what is AST1. Regarding AST2, the formula is ASC FSC divided by 0.87 Fy. So applying all these things, we can able to find out the AST2. Before which we have some condition is available for FSC, that is FSC in no case it should exceed 0.87 Fy. So if it is exceeding 0.87 Fy, means FSC will be equal to 0.87 Fy. That is, if FSC is greater than 0.87 Fy, means then FSC will be equal to 0.87 Fy itself. In no case it should exceed. Now let us go with a numerical example considering the doubly reinforced section. Here a rectangular reinforced concrete beam has been given with an overall size of 250 mm by 400 mm, which is located inside a building in a coastal town. And this beam is simply supported resting on two masonry walls of 230 mm thick, which are 6 meters apart in the center to center distances. Here the beam is said to carry a distributed live load of 10 kN per meter in addition to a live load of 5 kN per meter. In addition, again, its own weight also to be taken care. But in addition to all these distributed load, here the beam which is having a special case, it is also carrying a concentrated dead load of 30 kN, which is placed at the midspan point. So here the beam is not only subjected to distributed load but also a concentrated load. That small variation is also been given in this problem. You are supposed to design the beam section using M25 grade concrete and Fe415 grade steel. Now moving on with the design procedure, as always in the beam design, we'll start with the cross section definition. But in this case, the cross section is restricted with a value of 250 by 400 mm. Directly we'll move on with the second step, that is the determination of effective span. So we'll have two conditions are available to fix the effective span. One is the center to center distance between the supports, that is given directly in the problem. Second case is clear span plus effective depth. So here the center to center distance has been given. Therefore, the clear span has to be calculated. How to calculate this clear span is center to center distance minus the width of the support. That's what has been done here. Plus the effective depth, assuming an effective cover of 50 mm, we are assuming D is equal to 350 mm. That's what has been taken here. So getting these values, we'll have 6 meter is the first case and 6.12 meter is the second case. As per the Codal provision, we are supposed to use the minimum of these two, which comes as 6 meter. The second step is we'll be finding out the loads. As always, the loads will start with its own weight, the self weight. Here, the section details are 250 mm by 400 mm. Therefore, 0.25 into 0.4 into 25, which is the unit weight of RCC. We will get the self weight of the beam as 2.5 kilonewton per meter. Then the live load as well as the dead load which are acting on the beam are given in the problem with a value of 10 and 5 kilonewton per meter respectively. In addition, if finishing load is required, we can assume, or else we can leave that one. So summing up these values, you will be getting the total working load, the working distributor load of 18 kilonewton per meter. So this value will be multiplied with the load factor of 1.5 in order to get the factored load throughout the span, that is the distributor load of 27 kilonewton per meter. In addition to this distributor load, the beam is also being subjected to a concentrated load, that is the factored load at the midspan, which is 30 into the load factor of 1.5, which comes as 45 kilonewton. So while calculating the bending moment or shear force, both the loads has to be considered separately. The next step is the bending moment and the shear force. As we know, the maximum bending moment formula will be WU L square by 8 if it is a distributor load, and WU L by 4 if it is a concentrator load. Since in this beam, both the distributor load as well as the concentrator load are acting simultaneously, we need to calculate the moment separately for both the cases and sum up in order to get the total bending moment. So substituting all those values, we got the maximum bending moment as 189 kilonewton meter. Next, the limiting bending moment, that is MU limit. For Fe 415 grade steel, the limiting moment will be calculated by using the relation 0.138 FCK BD square. Substituting the values, we will get the limiting bending moment as 105.65 kilonewton meter. Now you can see here, MU is greater than MU limit. Therefore, the section will be a over reinforced section. But unfortunately, the cross section has been defined, which is restricted. For this case, we are not supposed to increase the cross section. Therefore, the beam will be designed as a doubly reinforced section. Next, the maximum shear force also will be calculated by the sum of the shear force for the distributor load as well as the concentrator load. So substituting the values, we will get the maximum shear force as 112.5 kilonewton. Next, moving on with the design of reinforcements. So here in doubly reinforced beam, the concrete resists compression up to its limiting capacity, whereas the excess moment is resisted by the compression steel. And therefore, the compression reinforcement is designed first rather than the tension reinforcement based on the excessive bending moment. And here the compression steel is provided not by choice but by necessity when moment demand is high. Let us go with the relationship which is given in your Annex G 1.2. That is MU minus MU limit will be equal to FSC ASC into D minus D dash, where FSC is equal to the stress related to a strain of 0.0035 XU max minus D dash divided by XU max. But if you want to calculate the stress, means this strain has to be multiplied with the Young's modulus of steel with a constant value of 2 into 10 power 5. And we know for Fe 415 grade steel, XU max value will be 0.48 D. So substituting that value 0.48 into small d is 350 and small d dash represents the effective cover to compression steel, and ES is the 2 into 10 power 5, the Young's modulus of steel. We'll get the value of FSC as 491.66. As already mentioned, FSC is having some limitation that it should not exceed 0.87 Fy. Here in this case, for Fe 415 grade steel, 0.87 into 415 represents 361.05. But in our case, whatever we calculated is exceeding this 361.05. Therefore, FSC can be adopted as 361.05 Newton per mm square itself. Now, substituting this FSC in this equation with all the values MU, MU limit, FSC, and then D and D dash, we'll get the value of ASC. That is the area of the steel in the compression zone. Now assuming the diameter of the bar, let me assume 20 mm diameter bar, providing 3 numbers as the compression reinforcement. Therefore, the area of the compression steel provided is 942 mm square. Now moving on with calculating the percentage of the compression reinforcement, 100 ASC provided divided by BD. So 100 into 942 divided by 250 into 350, which comes as 1.08. This is equal to, equal symbol is missing, 1.08 percentage. So once compression steel is calculated, we determine the total tensile force required. That is corresponding to the area of the tension steel AST. Here the tension steel resists the moment due to the concrete compression as well as moment due to the compression steel. Therefore, the tension steel is always higher than in singly reinforced beams. So let us start with the AST1 calculation. That is the area of the steel required for a balanced singly reinforced section required for limiting moment calculation. That is MU limit. This formula is available in Annexure G 1.1b, wherein we replace the MU by MU limit. All other values are known. You can substitute the value in which AST1 is the unknown. We will get a quadratic equation in terms of AST1. Solve for it. You will get the minimum value, the two values out of which the minimum should be taken. That is 1043 mm square. Next, the area of the tension steel that are required to counteract the compression steel to be calculated, that is AST2, which will be calculated using the relation ASC FSC divided by 0.87 Fy. All the values are known. Just substitute. We will get the value of AST2 as 770 mm square. So the total area of the steel in the tension zone is AST1 plus AST2, which comes as 1813 mm square. Now we will check for the minimum percentage of the steel, that is 0.85 BD by Fy, which comes as 180 mm square. The value of AST provided is more than the minimum requirement. Hence we can provide the as such calculated value. Now we can assume the diameter of the bar. Here in this case, I am assuming 4 numbers of 25 mm dia bars as the tension reinforcement, which provides a AST of 1964 mm square. The next step will be the check for the shear, in which we'll start with the nominal shear stress. Tau V will be equal to VU by BD. Everything is known. Substitute that one. You'll get the value of nominal shear stress as 1.29 Newton per mm square. So this value should not exceed the permissible shear strength, for which first we'll be calculating the percentage of the tensile reinforcement, that is 100 AST provided by BD. So substituting the value, we are getting the percentage of tension reinforcement as 2.25. So from table 19 of IS 456-2000, for different percentage of steel and for different grade of concrete, in our case it is M25 grade concrete, and the percentage of steel we calculated as 2.25. The corresponding tau Z value, that is the permissible shear stress in concrete, is being computed as 0.85. is what has been given here. Now the permissible stress is 0.85, whereas the calculated value based on the loading is 1.29, which means it is exceeding the permissible limit. Thereby, the shear reinforcements are to be designed separately. Now moving on with the design of shear reinforcement, we need to calculate the balance shear. That is the total shear acting on the beam minus the shear taken by the concrete. That is tau C BD. Substituting the values, we are getting the balance shear as 38.125 kilonewton, for which only we need to design the stirrups. Now assuming 6 mm dia 2-legged stirrups, the spacing of the stirrups can be calculated using the relation 0.87 Fy ASVD divided by VUS, in which VUS is the balance shear, Fy is the characteristic tensile stress, ASV is the area of the vertical steel, and D represents the effective depth. Substituting that values, we will get the spacing as 187.4 mm. And this has to be checked with the two conditions. One is 0.75D as well as maximum limit of 300 mm. So this value is less than the maximum limit of 300 mm, as well as it's less than 0.75D. D here in this case is 350. 0.75 into 350, we are getting the value as 262.5. So this satisfy both the cases, let us assume 6 mm dia stirrups, two-legged stirrups at 180 mm centers, less than this one to be provided. It's some whole number. So we are providing 180 mm centers from the face of either support and then increase it to 300 mm centers at the midspan, as shear will be maximum at the supports whereas a minimum at the midspan area. Thereby the spacing between the stirrups can be increased at the midspan zone, whereas it can be provided based on the calculation at the supports. Now this is the reinforcement details. Since we are providing the stirrups at two different locations in a different spacing, we need to provide these stirrups in two different ways. One is at the support and the other one is at the midspan. Coming on to the support, we have calculated the stirrups as 6 mm dia at 180 mm centers, whereas midspan we are increasing the spacing from 180 to 300. That's a variation between these two cases. All other terms remains the same. Width is 250 mm, effective depth is 350 mm, overall depth is 400 mm. The beam is reinforced with 4 numbers of 25 mm dia bars as a tension reinforcement and 3 numbers of 20 mm dia bars as compression reinforcement. So once all the designs been done and all the checks been done, the final check is to be done for the deflection control. So the check for deflection will have the relationship L by D maximum will be equal to L by D basic into KT into KC into KF, where KT, KC, KF represents the modification factor for tension reinforcement, compression reinforcement as well as flanged section. For the percentage of tension reinforcement of 2.25 from figure 4 of IS 456-2000, we can calculate the modification factor for tension reinforcement, that is KT can be calculated. Here the percentage of tension reinforcement is known 2.25, whereas Fs is to be calculated. Fs is the steel stress of service loads. So that has to be calculated. The formula is available below that chart itself. It's been given as Fs is equal to 0.58 Fi divided by 0.58 Fi into AST divided by AST provided. So substituting the values, we are getting the FSE as 222. As we have the curves available for 190 as well as 240, let me calculate the value of this modification factors for both 190 and 240 and then interpolate for the exact value of 222. We are getting the KT as 0.85. So this is known, this is 0.85. And since this beam that we are designing is a rectangular beam, there is no flanged section and hence this value will be taken as 1. The remaining term to be calculated is the modification factor for the compression reinforcement. So for PC, percentage of the compression reinforcement of 1.08 from figure 5 of IS 456-2000, we can see the percentage of the compression reinforcement which is available in the x-axis, and y-axis represents the modification factor for compression reinforcement. Since PC is 1.08, expand that one and we have only a single curve, not like the KT curve. Project that one with respect to the horizontal, we can get the modification factor which comes as 1.27. Now KC is also been calculated 1.27. Now substitute these values and L by D basic for a simply supported beam. Here the beam is a simply supported beam. L by D basic will be 20. So substituting all the values, we can get the maximum L by D ratio of 21.59. Here the actual L by D ratio is effective span is 6000, that is 6 meter, divided by effective depth is 350, which is 17.14. And this value is less than the limiting value of 21.59. And therefore, here the beam deflection control is satisfactory. So let us summarize today's lecture. Here, doubly reinforced beams are used when the depth is restricted. Here, the compression steel increases the moment capacity as well as ductility. Design involves similar to that of the singly reinforced beams such as flexure, shear as well as the deflection checks. And these type of beam are common in continuous beams, bridges or heavy load carrying structures. So far we have discussed the design of RCC beams using the limit state method, starting from singly reinforced beams and then moving on to the doubly reinforced beams. as beams are one-dimensional flexural members that primarily carry loads along their span. In the next lecture, we'll move to another very important structural element called the RCC slabs, which are two-dimensional flexural members used extensively in buildings. Thank you.